We know that at relativistic speeds and around astronomical bodies, time seems to slow down, expand, dilate. The question is, what is the connection between time dilation, velocity, and proximity to masses? In this video, I will try to connect these factors together and present a physical description of time dilation without relying on the shape of spacetime. Based on this slide, you may bypass any section or slide you feel maybe you're familiar with. I don't recommend this since the entire presentation is intertwined, but given the extensive length of this presentation, you may want to fast forward to the summary of this presentation just to get a gist of the topic. In Newtonian mechanics, time is undefined but absolute. 1 second on Earth equals 1 second everywhere in the universe, regardless of where you are or what you're doing. The concept of time dilation originated with special relativity. Einstein's equations of the special theory of relativity modified the concept of space and time to keep light speed constant for all observers, and time dilation appeared in the equations. Physically, he couldn't give a valid reason as to why the speed of light was constant, but universal expansion was unknown to him. Minkowski reformulated special relativity by combining space and time into spacetime. This also led to time dilation effect due to proximity to masses in general relativity. Now, time dilation is real. It can be proven. In the upper atmosphere, cosmic rays, which are mostly high velocity protons, hit the air and create pions, which decay into fast moving muons. These muons have very short lifetime. They shouldn't reach the ground, but they do, which means their lifespan is expanded or their time delays because of their high velocity. Meanwhile, operators of GPS satellites have to constantly update the clocks on the satellites to compensate for the difference in orbital distance between satellites and the Earth's surface, as well as the satellite's orbital velocity. In this case, time delays because of distance and velocity. YouTube has too many excellent videos on the standard interpretation of relativistic time dilation, so I'm not going to include one. But what I noticed is that all videos explain time dilation in terms of geometry. It's as if time dilation is equivalent to its geometric interpretation. None of the videos provide a physical description of time dilation. None of them discuss a physical reason as to what time is or what causes it to dilate, except to say that time is a dimension. In this video, we'll try to give you a physical reason for time dilation. To get started, I need to define a few terms. We're conditioned to believe the Earth or the stars are stationary. Nowadays, we believe that stationary only means that two or more objects are not moving relative to each other, or they are moving in the same speed and same direction within the same frame of reference. Based on this, we can say there's no place we can call stationary. Everything moves compared to something else. Since time depends on velocity and everything is moving, all objects have their own time. In other words, we can generalize the statement as time evolves differently for different observers. At this point, I need to define the meaning of three major physics concepts: space-time and space-time. Google defines space as a three-dimensional continuum containing positions and directions, although quantum mechanics defines space as a set of fields, each manifesting a particle. Time is defined as a measure of the interval between two events, although in relativity it's a dimension, while in quantum mechanics, time is undefined except to say it may arise from entropy. As for spacetime, it's a relativistic mathematical model that combines space and time in a four-dimensional continuum, but mass can bend this mathematical model. And this is the point where I lose my readers. But stay with me. Relativity was published and interpreted before universal expansion was discovered, and I need to include this discovery into my presentation. To me, the fabric of space is like a pixelated fluid that fills the universe with a constant density. Although around masses, this fabric gets concentrated at a rate of 1 over r squared, meaning the closer to the mass, the higher the space density, and the slower the expansion of the universe. Light and matter that happen to be crossing into this denser space slow down and smoothly refract toward the normal. On their way out, they smoothly speed up and change direction away from the normal. This velocity change depends on how fast universal expansion is at that particular point in space. That's why Mercury precesses and starlight seem to bend as measured in 1919 by the Eddington solar eclipse expedition. Since universal expansion will stretch and eventually rip space, something that hasn't happened for the past 14 billion years or so, the universe must be creating space-time pixels to plug the smallest possible rip that begins to form while also maintaining a constant density of the fabric of space. So to me, space-time is not a set of dimensions, but the constant, continuous, simultaneous creation of pixels of space and time throughout the universe. As for time, we don't have a physical description except to say it's a dimension. So let's use the formula for Planck's length to see what physical time may be. The top equation on the right side uses Planck's constant, gravitational constant, and the speed of light. The second one is just distance equals velocity times time. For velocity, I use the speed of the light, and for time, I use the Planck time. Since their value is the same, I set them as equal. Then square both sides to remove the square root and multiply both sides by c squared. Now, awkward as it may seem, dimensionally, both sides of the equation reduce to meters squared per second, a rate of virial expansion, which is a flux-like quantity. Since C4 is a constant, and Hg and C is a flux-like quantity, time can be considered a momentary field created simultaneously with a space pixel. As an analogy, think of what would happen if you could instantly create an electron from nothing. Remember, a moving charge creates a magnetic field around itself, but the magnetic field disappears when the charge stops. Therefore, an electron growing can be considered a charge moving. So, as the electron starts from nothing and expands to its size, a magnetic field expands around it. When the electron stops expanding, the magnetic field collapses back to nothing. Time will be created the same way. As a space pixel expands from nothing, a time field expands around it. When the space pixel stops expanding, the time field shrinks back to nothing and disappears. In other words, the time field disappears instantly, but the space pixel remains to enlarge the universe. So if you look at it this way, the Planck length is this diameter of a time field. In this definition, time is just a miniature field that appears and disappears everywhere, constantly, simultaneously, when new space is created by universal expansion. In other words, the creation of a new pixel space is accompanied by a moment of time. Of course, this momentary creation and instantaneous retreat of a time field implies that only the now, this moment, exists, and neither the past nor the future can exist, making time travel impossible. Now, unlike the stretching of an elastic band, which, when pulled, stretches more at the edges and less in the center, All time fields everywhere in the universe are created simultaneously, with no delay between them. The creation of any two time fields anywhere, it's as though the universal expansion is instantly transmitted throughout the entire universe. As a former science teacher, I'm fond of visual analogies to describe concepts. So imagine space as a black, three-dimensional expanding void in which light dots appear everywhere constantly for Planck time. To me, the universe is analogous to a giant screen in the old TV tuner tuned to channel 3. If you only experience flat screen displays, ask your grandparents to explain this. The flickering bright dots are space-time being created. So if you film the TV screen and then play it at fast forward, you will see a screen that's constantly lit. That's what we experience everywhere, a constant time glow surrounding us. In this analogy, space is the black background on the screen, and the glow is time evolving at a fixed rate around us. Once a time pixel fades, only the enlarged black fabric of space remains. To continue our analogy, moving at relativistic speeds would be similar to slowing down the fast forward setting of the video. In other words, at low velocity, the screen is totally lit. At relativistic speeds, dots appear to be blinking furiously around you. Approaching light speed is analogous to slowing down the fast forward some more, and the dots will appear to blink slower everywhere. If you're traveling at light speed, that's equivalent to stopping the film, and the traveler is in the same dots, the same moment. At that moment, to the traveler, time seems normal and he just reached his destination in an instant. But to someone watching from outside his frame of reference, the spacecraft is moving at light speed, but the traveler seems to be frozen in time. For the younger generation, let's change the analogy by saying there's an infinite field of 1 square inch LEDs cycling at 100 times a second, and you can film them. If you play back the film at regular speed, you'll see a constant glow. The blinking is too fast to be noticed. That's equivalent to traveling slowly over these lights. If you slow down the film to 50 frames per second, the lights seem to flicker at 50%, a rate of on and off every second. That's equivalent to traveling at 50 inches per second over the LEDs. At 80 inches per second, the flickering is 11 hertz. You are moving at 80% of the speed at which the LEDs are flickering. At 100 inches per second, the lights are always on to you. The traveling is in the same blink, time stopped, and you're in the same moment. And since light has a finite speed, light from distant LEDs will be reaching you after a delay that depends on distance. And this previous analogy is clearly flawed, since the traveler and the LEDs are in the same time frame. Time evolves equally for both. So, unlike flying over LEDs, time flickering cannot be noticed by a traveler, since the chemical reaction we call life slows down with increasing speed at the same rate as our perception of time and events. Nevertheless, at light speed, a traveler will be moving and living in the same instant. In slide 12 and 13, I described the analogy between a magnetic field expansion around the creation of an electron and the time field expansion around the creation of a space pixel. Assuming electrons were constantly created everywhere in the universe, regardless of your location, you would always be surrounded by a magnetic field. But if you moved, the expansion of these fields would slow down since their expansion depends on the relative velocity between you and the newly created electrons. The faster you moved, the slower these fields would expand. If you moved at the same speed as the electrons are created, from your perspective, the creation of magnetic fields would cease, since there would be no new electrons being created. Similarly, at the speed of light, space pixel creation stops, Therefore, time fields creation ends. No more new spacetime. To an astronaut lighting and dropping fireworks inside a 1G accelerating spaceship, the fireworks appear to fall to the propelling end of the spaceship and explode as if it was on the Earth's surface. As long as the spaceship maintains a 1G acceleration, this dropping and exploding is consistent, even though the spacecraft velocity is exponentially increasing. With a 1G acceleration, the spacecraft could reach 99% light speed in about 2.5 years. But to the astronaut, the fireworks will fall and explode at the same rate. The astronaut that's accelerating 1G sees the firecrackers fall and explode predictably. To him, the physics of the falling fireworks and the resulting chemical explosion seem normal. Because the acceleration, as its velocity increases, the firecracker's trajectory, chemical explosion, and the astronaut's metabolic rate slows down. Therefore, to him, fall and explosion appear normal. So faster velocity equals slower explosion and slower metabolism. But to him, everything is as always. When he reaches the speed of light, he's not aware of being frozen in time. But to an outsider observer watching the events inside and outside the spacecraft, everything unfolds differently. The observer can measure the velocity of the spacecraft, its furnishing, and occupants, and they're moving at relativistic velocity. But he sees the fireworks fall slower, the explosion evolve in slow motion, and the astronaut moves slower. That's because the spacecraft crosses time fields faster than space-time is created. Note, time dilation can only be noticed from outside the spacecraft, and of course, the assumption here is that it's possible to look inside a spacecraft moving at relativistic speeds. So, faster velocity equals slower fall, slower explosion, slower metabolic rate. At light speed, all these variables are frozen in place. So, just like the infinite field of blinking lights, at light speed, the astronaut and the fireworks are in the same moment, and no motion can be detected by the outside observer. Notice I never mentioned clocks or any other time measuring device. So let's look at why masses affect time. In slide 9, I proposed masses condense space around themselves, making space density higher at a rate of 1 over r squared in and around all masses. The higher density slows down universal expansion. Therefore, it slows down space-time creation around masses. With less space-time being created, less time is created, meaning time around masses dilate. Its evolution slows down. The greater the mass, the slower time is created, or time dilates more. In this picture on the right, the darker area represents the higher space density concentration, with mass being somewhere inside the dark shading. Notice that the shading is continuous from very dark in the center to white at the edges. The darker the shading, the slower space-time creation. At the center, time and universal expansion are at a minimum for that mass. So time dilation seems to depend on two factors, motion and proximity to masses. If an object is moving at a rate equivalent to space-time creation, it experiences time dilation or the slowing down of time. If an object is near a very massive object, it experiences time dilation because less time is created around it. Basically, time dilation depends on the creation of space-time, which depends on universal expansion. So let's look at the twin paradox as it's usually presented. Bob, a twin, is sent on a relativistic trip and returns home a number of years later, while Mary, the other twin, remains on the Earth. By the way, they're not identical twins. Since Mary is at rest on the Earth, Bob's time must dilate. But from Bob's perspective, Mary is the one who's moving, therefore her time should dilate. Still, when they're rejoined, Bob is younger. That's because we remain at rest with the Earth, and both Bob and Mary originated in the same frame of reference, the Earth, and reunited back on the Earth. Let's add a third frame of reference to this paradox. Bob and Mary are in two spaceships at rest relative to each other. In the distance, an alien measures the two spaceships moving at relativistic speeds away from him. Bob fires its engines and heads toward the alien until he's in the alien's frame of reference and begins to aging at the alien's time frame rate. The question now is, from which individual perspective? Who aged less, Bob or Mary? While Bob and Mary were in the same frame of reference, both aged at the same rate. After ignition, Bob saw Mary speed away from him. Therefore, Mary's time dilated. Mary was aging slower than Bob. Mary saw Bob speed away from her. Therefore, Bob time dilation dilated. Bob was aging slower. The aliens saw the distance between him and Bob decreased, meaning Bob slowed down. But Mary continued at her usual rate. Mary was aging slower. And if we change the alien's perspective, we can make Bob age slower. See, the paradox is created because of two implicit assumptions. Time is assumed to be constant relative to some undefined frame of reference, with everything moving through time, and we tacitly assume the Earth to be the frame of reference. If we remove the Earth and substitute it with a third spacecraft, we have the Bob and Mary paradox. In summary, time is a momentary field created by universal expansion everywhere, constantly, as a component of spacetime to prevent universal expansion from ripping space apart. Since everything is in motion and time is affected by velocity, everybody experiences time differently depending on their velocity or proximity to masses. At high speeds, an astronaut metabolism slows down, but that's only noticeable to outsiders. The astronaut doesn't experience time dilation. To him, everything proceeds at a normal rate. So, relativistic velocity implies motion approaching the speed of time creation, whereby time appears to slow down. Around masses, universal expansion is inhibited, which slows down spacetime creation, which translates to dilated time. From this perspective, time dilation depends on an object's speed compared to the rate of spacetime creation, as well as the actual slower spacetime creation around masses. Time dilation, therefore, depends on spacetime creation, which is a result of universal expansion.